Today's episode is brought to you by Engineering.com, a globally trusted source for engineering content. Check out this and many other exclusive videos for the engineering professional found only on Engineering.com TV today. Hello everyone and welcome to The Primary Loop, presented by Engineering.com. I'm Jim Anderton. I'm joined today by James Walker, CEO and board member of NANO Nuclear Energy Incorporated. Mr. Walker is both an engineer and a nuclear physicist with extensive experience in the submarine, nuclear power, mining, manufacturing, and automotive industries. James, welcome to the program.
Oh, thank you very much, Jim. Thank you for the introduction. Very generous.
James, it's you're at the forefront of something which is on everyone's lips today. Of course, this is carbon-free, CO2-free energy generation, and we know that nuclear has seen a recent resurgence. New reactors just opened in Finland, but SMRs are seen to be the bright spot in the future. The idea of getting away from these large mega projects and very, very complex projects. I understand at NANO you have a technology which is somewhat simpler and easier to sort of manage than these sort of conventional nuclear mega projects. Tell me about it.
So that nuclear resurgence is what brought me back into nuclear, and coming back into an industry that's very well established, and we had to take a very commercially minded view of what the market was. And obviously there are big companies like NuScale making fairly large SMRs. We took the attitude that potentially the biggest market was very small reactors, so they're technically micro reactors. Below the 10 megawatt range. And we realized this had potential to be distributed, potentially making thousands of these things a year. Remote mining projects, remote oil and gas projects, remote industrial projects, remote habitation, desalination plants, remote hospitals, anything like that. This small reactor could replace diesel generators for. So obviously we came at it from this angle that we wanted a reactor that could be distributed easily, transported easily using existing transportation infrastructure. And that was actually the basis of where we started. We didn't start from the design, but once we had an idea of the business model, we reached out to the technical teams. We brought in the University of Cambridge, the nuclear chair there, the nuclear chair of the University of Berkeley. And we brought on what we reckon is the best technical team in the world. And we started looking at reactor designs that could cater to this potential market. And the Zeus reactor was assembled, and that was a reactor that we wanted to shrink right down, and that meant removing as much of the working parts as possible, the pressurizer, and we even ended up removing the coolant from the reactor. And that was made possible by certain advances in material science, but also from a safety perspective, in that we didn't want to, one of the major failings of reactors could be coolant leak leading to core melt, which can obviously lead to a much more tricky cleanup operation. We wanted to have a passively cooling system that didn't have any possibility of coolant leak. You could essentially even smash this thing up if you really wanted to, and you wouldn't have a massive nuclear fallout or sort of any sort of danger coming from it. That's really where we came from with this.
James, I'm glad you brought up that notion of cooling, because we think of conventional reactor designs, heavy water, light water. Generally, it's we have a fueled reactor core, we have control rods. When control rods are mechanically actuated in and out to control the reaction, an emergency shutdown system to scram the reactor involving driving those rods in. We might dump boron compounds in there to poison it if we have to, an emergency. Layers of technical devices. Then for cooling, of course, we're extracting the heat with a primary loop, as this show was named, and a secondary loop, of course, to extract the heat and leave the radiation behind. So these are pumps and channels and valves and monitoring systems layered one atop the other. How do you do this with no working fluid extracting the heat from the reactor?
So, I mean, my history is mostly PWRs as well. And, if you are going to build a big reactor, you do need all of those safety mechanisms in place. And there's no real way around it. But when you do go very small, the first thing that, you're going to have to look at slightly more enriched fuel than you would be looking at for that sort of conventional gigawatt power PWR that's feeding into a city grid. So you're going to be looking at sort of a HALEU fuel just enriched to about 19.75% beneath that 20% limit. gives you a slightly higher power density. And obviously then you've got to look at removing that heat. But one of the advantages actually, when you do shrink it right down and you have less power to distribute, is that then suddenly if you have we put a thermal conduction mechanism in there. So we just conducted the heat through a solid core. And the solid core enables us to, first of all, remove that coolant, but then other benefits fall out from that. So once you remove that coolant, you can remove the pumps, another big mechanism that could go wrong and obviously create enormous reactor issues. That we also were able to move the pressurizer. And then as soon as you start removing all these things, then the working parts within the reactor that could potentially cause issue all shrink right down. And we've essentially, we think we've got to the most simple design that is possible. I mean, I'm sure the future will prove us wrong, but at this point in time, you can't really get much more simple than what we're trying to do. It's just a nuclear battery almost, that it's going to be very low power, catering to not city grids, but as I said, those remote projects. Could do military bases, remote habitation, but essentially that's the benefit of going really, really small.
James, you mentioned materials, and of course, one thing we know is that neutrons play hell with reactor materials. I mean, you could spend an entire career observing what happens to zirconium in the presence of these things. How have you solved that problem there? Do you use exotic materials in this reactor?
So, I mean, for the solid core matrix was the most important part because we needed to be able to sustain heat emanating from the fuel rods of about 900 degrees. So originally we looked at aluminum nitride, which had good thermal conduction properties. But we're also now looking at beryllium oxide as another good mechanism to conduct heat through. Conducts heat very, very well to the periphery of the core. Obviously, we allow for some thermal expansion of the control of the fuel rods. So as it obviously gets hotter, a lead eutectic just around that, but a very thin layer, separating the solid matrix, the beryllium oxide solid matrix from the nuclear fuel rod. But that's essentially it. Shield reflector. You can actually again use beryllium oxide for that. But the simplicity of our core, of our design is the fact that we don't actually need a huge amount of materials in this. One thing we wanted to do is to keep things simple is that when it came to the fuel itself, we wanted to go for a very weathered and known fuel type as well. So we just went for uranium dioxide. And I know other SMR companies are going for more exotic fuel types. A lot of triso goes into there, but the data set for those aren't as well known, and sourcing those things and fabricating them are a lot more difficult. And we wanted to go basic to prevent any future technological issues with regard manufacture or sourcing or fabrication and eliminate that. But that's essentially where it drops down to. So uranium dioxide, conventional fuel rods, thin lead eutectic just to allow for a small amount of thermal expansion, and beryllium oxide, solid core, thermally conducted to the periphery of the reactor to remove, and then the heat gets removed through essentially air circulation to a gas turbine. And that's the totality of it. So.
James, it sounds very simple. Is there a possibility of using this for process heat as well as for electricity generation?
Oh, absolutely. So, I mean, the advantage here is that, I mean, with nuclear, unlike, say, wind or solar, and not to downplay those, obviously you can cycle up power and cycle it down as you require. But at these higher heats, you could do things like hydrogen generation, for instance, because it's almost perfect for that kind of process. So if you didn't want to have an electrical output and you didn't want to have that turbine creating that electricity, you could just utilize the thermal output, and obviously the thermal output would be higher than the electrical just because of losses involved in the turbine system. But yes, absolutely, it'd be almost better than the conventional large reactor, which operates at lower temperatures.
Are your reactors fueled and refueled on site, or is this something that sort of arrives as a unit and is sent back to the factory?
So the plan actually is to deploy the reactor, and it would have an operating life of about 20 years without needing any refueling. There's no plan to refuel at site. And the business model will involve shipping a reactor out. And the good part about this is that, say you have a very large reactor, that needs to take into account the environment it's being shipped to, including the landscape, all the environmental factors. When you get very, very small like this, the process becomes essentially a deployment of an entity that can be placed down, and the environment is not irrelevant, but it's far less a factor in the commissioning process. The reactor would run for as long as you needed it at that business or industrial operation or remote habitation. Once it was finished, it would then be, it's still contained within that shipping container, and then it would be shipped back to us for disassembly. There wouldn't be a long decommissioning process at the site. And that's one of the big potentially commercially interesting things for customers with this as well. It's as you need it.
James, well, how about the staffing requirement to monitor and operate this reactor? Of course, we know in nuclear submarines we have a dedicated reactor crew. In the early 1960s, a air transportable reactor was sent to Antarctica in support of a U.S. Navy research team, and I believe that small reactor required, I think, 7 or 8 technicians to operate in shifts to monitor this thing constantly. How does yours operate?
I know about that reactor, actually. I was very interested in it. But with ours, actually, you would need fewer than that. What we anticipate is, because we envisage manufacturing a lot of these, is that we would actually have a central base, a central hub where you would have the majority of the NANO workforce monitoring all the reactors that were deployed. And so they're obviously looking at transient behavior, obviously thermal behavior, and can monitor safely, because a lot of these things could be remotely managed. 7 or 8, we probably won't need that many. You would always need someone physically at site to physically intervene in things where there is a mechanical or digital failure, for the central hub to monitor and control. That job might be quite boring for whoever gets assigned to it, because they probably wouldn't be doing a lot. But you would really only need perhaps 1 to 2 people per shift, just monitoring the reactor, because most of the work would be done by a central hub.
Brilliant. I have to ask the question, of course. You're a physicist, you're an engineer, but money is always a factor in electricity generation at this point. What sort of orders of magnitude of costs are we looking at here? We know that conventional reactor designs are mega projects. There are billions of dollars involved. They frequently have very large cost overruns that can take a decade or more to get up and running. In relative terms, what are the costs of your NANO system compared to, say, a thermal power plant of equivalent capacity?
So, I mean, the good part about going small is that, say, when you have a large power plant, is that I would say up to 50% of your costs would be on the interest related to the large amounts of financings that you would take to put that plant into production. So already we eliminate those large capital costs and the associated interest that would come with those. So the actual costs diminish for us very quickly, because the costs are so much smaller. Now, obviously, we don't really want to. It's difficult at this moment to accurately put a dollar per gigawatt or dollar per megawatt on the reactor. But when I think I can't remember the organization that did the evaluation. It might have been Bloomberg, but when they took into account SMRs and the green subsidies that were being put on zero carbon emitting technologies, the cost of technology became very commensurate with the price of gas for the SMR level. And that's principally where we will be looking to produce that kind of cost estimate, that kind of cost range.
That's an exciting future. James Walker, Nano Nuclear Energy, thanks for joining me on The Primary Loop.
Oh, thank you very much for having me, Jim. Thanks.
Well, that's it for this episode of The Primary Loop, brought to you by Engineering.com. For our deeper engineering series, visit engineering.com TV for exclusive shows like Manufacturing the Future, Designing the Future, and the Engineering Roundtable, not found here on our YouTube channel. The links are in the description below. Thanks for watching.